A phase diagram is a graphic way to summarise the conditions under which equilibria exist between the different states of matter. In the diagram, pressure and temperature are plotted on each of the axes. There are areas on the graph that represent different states of matter, which are separated by three main boundaries. This boundary represents the equilibrium between the solid and liquid phases. If a substance is solid and transitions to liquid with varying temperature and/or pressure, the substance undergoes melting. The opposite process is called freezing. This boundary represents the equilibrium between the liquid and gas phases. If a substance is liquid and transitions to gas with varying temperature and/or pressure, the substance undergoes vaporization. The opposite process is called condensation. The final boundary represents the equilibrium between the solid and gas phases. If a substance is solid and transitions to gas with varying temperature and/or pressure, the substance undergoes sublimation. The opposite process is called deposition. The point where all the curves meet is known as the triple point. At this point, the substance will be in equilibrium with the solid, liquid, and gas phases. We can use the phase diagram of a substance to explain or predict what phase it will be in at any given temperature and pressure. For example, watch as we leave solid water and solid carbon dioxide on the lab bench to heat up. At normal atmospheric pressure, water forms a puddle of liquid, whereas carbon dioxide does not. According to phase diagrams, we are seeing solid water melt, where it crosses the solid and liquid phase boundary, and we are also seeing solid carbon dioxide sublime, where it crosses the solid to gas phase boundary. The boundary between the solid and liquid phases for carbon dioxide generally slopes towards the right, with increasing pressure, as you can see here on this phase diagram of carbon dioxide. This tells you that the melting point increases with increasing pressure. Therefore, the more compacted or dense the solid, the more energy to melt the solid to its liquid phase is required. In contrast, this boundary in the phase diagram for water atypically slopes towards the left, with increasing pressure. This indicates that the melting point decreases with increasing pressure. Water is thus less dense in its solid state compared to its liquid state, which is why ice floats in a cup of water. In experiment 4, you will construct a phase diagram of tertiary butyl alcohol. When heating, use boiling chips or anti-bumping granules, which are small porous stones that allow even boiling. This is a sufficient amount. When observing the boiling point of tertiary butyl alcohol, start the timer and your recordings only when your alcohol effervesces. Leave the timer running when transporting your alcohol and continue recording temperature every 15 seconds until it reaches 10 degrees Celsius. Setup for observing the triple point of tertiary butyl alcohol involves connection of a water aspirator to a vacuum flask. This is connected to your tertiary butyl alcohol. The system is sealed with rubber stoppers and you may read temperature from the thermometer. Remember, conceal, cover, concentrate.